Hey guys, thanks for tuning into CMTEQ channel once again in the series of tutorial on short circuit MVA calculations, electrical protections and power system distribution, and ensuring that the electrical grid is at all time functional and operational is the most important thing for any economy or any country to prosper. Because without a stable electrical supply, nothing can really function in a modern economy. Things will start going down. Now, enough of that discussion. This tutorial is obviously for a power system technician or an electrical engineer who's responsible of ensuring that there is electricity available without interruption. Now here you have a network, a power system network, obviously that is comprised of a generator. This generator obviously can be modeled to be your thermal power plant, hydroelectric or solar. Then you have a transformer that need to step it up for long transmission, because we all know you cannot transmit with low voltage. Otherwise, there are going to be a lot of losses because you need to transmit the power that your generator is producing. So if this generator is producing 50 MVA, that is a lot of power. So which means there is a lot of current here that need to be transmitted. So if you do not step up your voltage so that the current can decrease, then you're going to have a lot of losses into your transmission line. So in order to mitigate that factor, we use step up transformers for transmission line. So here we have that, and as you can see, this generator G2 is also supplying 100 MVA, right, and at 11 kilovolt, and it is also stepping it up to 33 kilovolt for transmission line. Now both generators are basically converging, so they are supplying to the grid and to the transmission line to the load here. So we've got a load here at load A. Now before the load there is a transformer T3, right? Because we need to take this voltage and step it down to a level that is suitable for low power or low voltage distribution. All right. So this tutorial basically here, they want us to find the short circuit at this point here. Okay. Because why is it important for us to determine the level of the short circuit here? And that is because we want to ensure that we can provide the protection when it happens. If you do not know what is the level of your short circuit, it will be difficult for you to spec a circuit breaker that can break it and prevent fire or explosions. So a lot of things can go wrong. So now in this tutorial, we basically, as always, we're going to convert this network here into a per unit system. All right, so that is a per unit impedance diagram, and that will basically make it easier for us to trace which path the current will take, and from there we can determine the current magnitude or the MVA short circuit magnitude at any particular point. But for here, we are interested into the short circuit at this particular point here, which is the secondary of T3. Now moving forward, if you found this tutorial interesting and useful, please give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated, and I thank you very much for your support. We know the general formula for getting the per unit value of any electrical component. So the idea here is that we are moving from an old base system to a new base system. So this is why you can use any MVA here to solve this problem. So long as you maintain it, you're going to get exactly the same values, because you basically will be making a transformation from an old to a new system, and everything should work out if you respect the formula and all your transformations. Just now, the base voltages, they vary per zone, so they cannot remain the same, because remember, you are moving from generator voltage to transforming the voltage, stepping it up or stepping it down. So at any particular zone, you have to look at what is the current voltage at that zone before you can proceed with your calculation. So having said that, we deduce then that for generator 1 here, okay, using the 50 MVA, we can get the new Z per unit to be 0.3 2J per unit. Now you'll see that it is exactly the same thing as what is given here, and that is precisely because we have 50 MVA for this generator, and we also have 50 MVA for the new base that we are using. Now, if you want to use 100 MVA, then you're going to get a different value here, but make sure you maintain it throughout the system. Now, moving forward, T1 Z per unit new is 0.12 J per unit, and for generator 2, Z per unit new is 0.085. The transformer that follow, that is T2, is 0.05 J per unit. Now moving on, we then need to find Z per unit new for this transformer T3 that is supplying our load A here. Now, one thing that we can notice here is that transformer 3 have a different voltage ratio, that is 40 on the primary and 11 kilovolt on the secondary. That is different from this transformer, and that is also because now power is flowing this way, right? Power is flowing this way to come to the load. So which means because the line voltage here at this point here is 33 kilovolt, that is coming from these two transformers T1 and T2 that are basically transmission line transformers. Now, because the transformer T3 here have a different ratio, right? So now the assumption here is that this transformer with a 40 kilovolt and 11 kilovolt ratio was used in a transmission line system that had also 40 kilovolt on the transmission line. Now we have a new transmission line that have a 33 kilovolt. So which means automatically VB new for this transformer need to change to correspond to what the line voltage here. Now to do that, we use a transfer function that we have to now say VB new for T3 must be equal to VB line, okay, so that is the line voltage from this side, times the inverse of the transformer ratio, so that is V secondary divided by V primary. And from there we can basically just deduce, because we know our VB line is 33 kilovolt, right? Our transformer ratio, the secondary is 11 kilovolt and the primary is 40 kilovolt. So we find a new VB new of 9.075 kilovolt. So you then have to use this VB new here into the Z per unit formula to calculate your Z per unit new for transformer T3, okay? And having obtained all your VB new and VB all being 11 kilovolt, you can then calculate Z per unit new for transformer 3, a new per unit for T3 to be 0.147 J per unit. Now, this is very crucial, because if you do not realize these different transformer ratio and adjust it based on what's coming on your line here, you're not going to get this VB new. So if you get a wrong VB new, or you use 40 kilovolt here as your VB new, then you obviously going to get a wrong Z per unit new for this transformer, and that is not going to spec it to have a correct short circuit current, because remember, your short circuit current depend on the per unit impedance diagram. So if you start getting wrong per unit impedance value here, that basically means you're gonna get a wrong short circuit current, right? Now, if you have any question, please drop your question in the comment box for clarification. So now moving on, we can then calculate our Z per unit new for the line. Basically Z per unit for the line, since we know that the line here, the transmission line, apparently have an impedance of J100 ohm. So that basically means it's purely inductive, right? It's purely inductive impedance on the transmission line. So it's 100 with a 90-degree angle. Okay, so now because we know what is our zone 2 voltage, which is 33 kilovolt, we can then go ahead and calculate our Z per unit of the line using the formula. Z per unit of the line is Z actual divided by ZB. Now Z actual is this impedance value here, okay, and our ZB, right, which is now the base impedance. Now remember, ZB base impedance is based on the voltage of the line, so which means we have to calculate it by using the VB zone, which is 33 kilovolt, divided by SB new, because this is the new MVA that we are using to spec our new system. Okay, now the calculation gives us a value of 21.78 ohm for ZB, and we can then go ahead and calculate Z per unit of the line to be equal to 4,59 ohm. So now we have calculated all the new per unit value for G1, T1, T2, G2, and T3. We can then go ahead redraw our impedance diagram. So our new impedance diagram is then going to be as follow. Now you can see we can start following the money, right? We can start following the path the current is going to take to this fault. Because remember, this generator 1 and 2, they were supplying to this load here, right? Now all of a sudden this load is demanding more because there is a short circuit that is there. So all the current from G1, T1, G2, T2 are now going to flowing faster to get to where to the short, because the current want to return to the ground, want to return to the source of generation. So the quickest path to do it is by going to ground. Now moving forward, we then need to reduce this per unit impedance diagram to something small so that we can obviously calculate our Z per unit total that is going to help us find the short circuit current at this point here. So from there we can basically reduce this circuit here. As we can see that G1 and T1, right, they are in series and they are also in series with the line per unit. So which means the combination on all of these should give us a value, and T2 and G2 are also in series. Now there is a junction here on bus bar 2. Why is there a junction? Because we have a fault here. So which means the current coming from this side and the current coming from this side, they are merging here to flow here at this particular point. Okay, so having said that, we can then get the following reduction. So that basically means T1 plus G1 plus the line give us 4,91 J per unit, and T2 and G2 give us 0,135 per unit value. So this is G2, okay, and on this side this is supposed to be G1. So now we've got our junction, we know the power is flowing this way, and here is our fault, and obviously this is T3, so make no mistake. Now from here we can see that since this is a junction, right, it's a node where the current is flowing to this point, that means the current is converging, right, from both sides. Okay, so the conversion, that means it's a parallel circuit here, so we need to calculate the parallel equivalence of this section and this value, and that basically give us T1 plus G1 plus line parallel to 0,135. So we get a value of 0,131 J per unit. So this will then give us a new network, right, reduced drawing per unit impedance, that then give us this whole combination, which gives 0,131 per unit, and we still have our T3 here, that is 0,147. So you can see that this and this, they are now basically a simple series circuit. So which means Z per unit total is the equivalent of these two combined. So that will be Z per unit total. So Z per unit total is obviously 0,131 plus 0,147. It gives us a value of 0,278 J per unit. Right. So from here, we can then go ahead and calculate I per unit, which is given by I per unit is equal to 1 over Z per unit total. We already know what Z per unit total, so we then just deduce 1 over 0,278 J, and we find an I per unit current of 3.597 amps, right? So that is the I per unit current. Now, we know to find the short circuit current, we need to multiply I per unit times the line current, okay? As per the formula, I short circuit is equal to I per unit times the line current. Now, it is important to know which voltage you're going to use to find this line current. Because remember, this line current here is where the fault is located, which is rated at the voltage on the secondary of this transformer. Remember, this transformer, it had a ratio of 40 over 11 kilovolt, but we changed this primary to 9.075 kilovolt, but the secondary of this transformer is remaining at 11 kilovolt here at this point. Okay, so which means this line voltage, okay, the line current must be calculated with the 11 kilovolt, not with the 33 kilovolt that is on the transmission line. So you have to distinguish that so that you avoid mistake. So having said that, we can then deduce our I line is equal to SB nu over VB zone, right? So that is the VB zone on this zone here, which is on the load zone. Okay, so that gives us 50 MVA over 11 kilovolt times the square root of 3. Okay, working on a three-phase system. So that gives us a current of 2624.32 amps. Right, now from that, we can then get our short circuit current at this point here. Okay, so I short circuit at this point is equal to 9.44 kilo amps. So that is I per unit times I line. Okay, so it's a massive short circuit current that is present at this point here. Right, so now we need to move to the main question, that is the MVA short circuit. So that is the megavolt ampere fault level at this point. So to deduce that MVA short circuit, we then need to use the short circuit current, okay, to calculate our MVA short circuit by making the MVA short circuit or S short circuit, which is the apparent power, the subject of this very same formula, making sure we also maintain the VB zone where it is occurring on the load side. Okay, so having said that, our S short circuit is a square root of 3 times 11 kilovolt times 9.44 kilo amps, and that gives us an MVA short circuit of 179.85 megavolt ampere, which we can obviously deduce to 180 MVA of short circuit. Now, before we close this tutorial, since we are getting a short circuit current, right, at this point here, which is 9.44 kilo amps, and from that we get that short circuit MVA. But now we can also calculate, based on the short circuit that we're getting here, how much short circuit current are we getting here? The generator is contributing G1, and how much short circuit current generator 2 is also contributing from these 9.44 kilo amps that we're getting here at this point. Now remember, here is a 11 kilovolt. It's at a secondary of the load transformer, right? And here it's also on 11 kilovolt, but this is on the output of the generator. But now, because this short circuit current is going through an impedance circuit here, so which means the current is being dampened, is being reduced. That is why we have this impedance diagram, so that we can know exactly what is the level of the short circuit current. So in order to find the I short circuit for generator 1, we need the per unit, right, of generator 1, so that we can find the I per unit of generator 1, and then also deduce the line current that is coming out of the generator, and that is going to give us a value of the short circuit that is coming out of the generator 1. Now, please do not mix up between the short circuit current coming out of the generator, right, when there is a fault here, and the line current coming out of the generator when there is no fault. Okay, that's two different things. So when there is no fault, this generator is supplying a particular current. But when there is a fault in the system, this generator is also supplying a particular current. So now we can calculate it by saying, okay, Z per unit for generator 1, we know it's 0.2 J per unit. So that means the I per unit for generator 1 is 1 over Z per unit of generator 1, which gives us a 5 amps. So we take the 5 amps, then we need to multiply with the line current for generator 1. So the line current for generator 1 will be calculated with the same formula. Then it is 2.624 kiloamps. Okay, so it is basically the same line current, but obviously at different locations since it's the same base voltage. Right, now from here we can then calculate that short circuit current to be 5 times 2624.32 amps, and it gives us the I short circuit of generator 1 to be 13,122 kilo amps. Okay, so we use the same method to calculate the short circuit for generator 2. How much short circuit we getting here? Okay, how much I short circuit we getting from generator 2? Now generator 2, we know that Z per unit is 0.085, so it's smaller, so which means we expect a much larger short circuit current. Okay, so you can see that I per unit for generator 2 is obviously 11.765. It's almost double compared to the one for generator 1. So that gives us then a short circuit for generator 2 to be 30,874 kiloamps. Obviously more than double. Okay, that tells the story from the I per unit of generator 2. Okay, so basically this is how you deduce all these calculations. And you can also calculate the short circuit current on the secondary of this transformer. So that basically on the line here, you can calculate the short circuit current here on the line, and you can also calculate. Now you have to understand that this point here, this is bus bar 2, so which means this impedance here was only denoted for this section here. So which means at this point here there is no impedance, so which means the value of the short circuit current here will not go through an impedance here. So if you have to get Z per unit total at this point, you're only gonna get T2 and G2. But obviously for here, you're going to get G1, T1 and line to get a Z per unit total, and then you can calculate the short circuit current at this particular point. And obviously they're going to be different, but they're going to merge here and be a much larger short circuit current. So you can get the question where they basically move the short circuit from this point to this point. Okay, so they can move the short circuit there. Then you need to be able to calculate the short circuit current based on all the level and the voltage of each zone. So that is it, guys, for this tutorial. I hope you've learned something, you found it useful. Don't forget to thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. So until next time, stay tuned for more complex tutorial on short circuit current and power flow design and all of that coming in the future on CMTEQ channel. Until next time, cheers.